Hi, I'm Karen Olsoy, licensed master esthetician, licensed instructor, and owner of Grove and Kane, a medical spa in Everett, Washington. Welcome to the Skincare Deep Dive podcast, where I take beauty professionals deep into skin biology to help you make real world clinical connections to serve your clients better. Today's episode is all about the melanocyte, the specialized cell responsible for producing pigment, and the remarkable chain of chemical reactions that ultimately give your skin, hair, and eyes their color. By the end of this episode, you'll understand exactly how one single amino acid gets transformed into pigment and how that pigment gets handed off to the surrounding skin cells. Look out for part 2 of this subject coming out soon, which discusses hyperpigmentation, or the irregularities in pigment creation that our clients come to us seeking to treat. But today is all about the mechanics of melanogenesis. Let's jump in. So first, let's orient ourselves. Your skin is made up of several layers, and the outermost living layer is called the epidermis. Look for my latest episode called Deep Dive the Epidermis for tons of education about our epidermis. Within the epidermis, the dominant cell type is the keratinocyte. Those are the bricks of your skin, stacked in layers, and they eventually migrate upward and shed from the surface, changing forms as they go. But nestled at the very base of the epidermis, in the layer called the stratum basal, or also called the basal layer, you'll find a far less common type of cell, the melanocyte. Melanocytes make up of only about 5 to 10% of the cells in the basal layer, but their influence is enormous. Each melanocyte extends long branching arms called dendrites that reach out and touch anywhere from 30 to 40 surrounding keratinocytes. This cluster, that one melanocyte plus all of the neighboring keratinocytes, is called the epidermal melanin unit, and it is a fundamental functional group of skin pigmentation. Here's a key point that surprises a lot of people. Everyone has roughly the same number of melanocytes regardless of skin tone. What differs between individuals and between different parts of the body is not the count of melanocytes, but how active they are and how much pigment they produce. And why do we need pigment in our skin at all? Well, let's think about color theory for a second. The dark color of melanin absorbs a wide range of wavelengths. So think about black leather on a car seat. Dark colors absorb light energy, which turns it into heat. And while light colors are going to reflect it, right? So melanin sacrificially absorbs and scatters UV radiation to prevent damage from occurring to our skin cells, because that dark color is really good at absorbing that radiation, thereby sparing the surrounding cell structures. UV radiation damages every part of our skin cells. That's also why after you've gotten too much sun, you can get itchy and rashy a few days after. This is because your keratinocytes are literally dying and shedding, which causes the release of histamine and other inflammatory mediators that are important in triggering melanogenesis. And this can happen even if you don't get burned. But the most important part of our skin cells is the nucleus. That is where the DNA of our skin or of each cell is stored. So if there's mutation to our DNA, that's how we develop cancer. And we're going to revisit this again at the very end of the podcast, but melanin is actually deposited into the keratinocyte in an umbrella-like fashion over the nucleus of our keratinocyte to protect the DNA below. So how does melanin end up in the keratinocyte? Let's dive a little bit deeper. So the journey of melanogenesis, surprisingly, actually is not going to start in the melanocyte. It's actually going to start in the keratinocyte. When UV hits your skin, the keratinocyte gets really stressed. Think of it like a house alarm going off. That alarm triggers the release of a chemical messenger called plasmin, whose job it is to basically like run down the street and bang on the door of the paint factory, the melanocyte, yelling, "Make more pigment, we need protection." But plasmin, so again, that's the chemical messenger that triggers the melanocyte. Plasmin doesn't just appear, it has to be made. And there's a sleeping, inactive version of it called plasminogen that's just sitting around in keratinocytes doing nothing. UV stress wakes up the plasminogen by sending out activating proteins that convert plasminogen into the active messenger plasmin. So the chain of events roughly looks like this. There's UV stress put on the keratinocyte. The keratinocyte releases activators. Those chemical activators wake up plasminogen, which turns it into plasmin. Plasmin then is the signal that causes the melanocyte to actually create pigment through two different pathways. So plasmin is going to cause the release of prostaglandin E2 and melanocyte stimulating hormone. And both of those messengers, the prostaglandin and the melanocyte stimulating hormone, finally turn the melanocyte on to create more pigment. As more melanin gets made, more gets transferred, the skin darkens, and that's what we call a tan. And again, that is an evolutionary mechanism to protect our skin from future damage, especially to the DNA of our cell, right? Because that melanin is deposited in an umbrella-like fashion to protect our nucleus. In hyperpigmentation disorders, this system gets dysregulated. Sometimes there's an overproduction of that melanocyte stimulating hormone or other stimulating factors. And sometimes there's increased sensitivity in the melanocyte signaling machinery. Sometimes there's impaired melanosome distribution. So there's a bunch of things that can go haywire in the melanogenesis pathway. And the result is going to be excess pigment. And that's what we call hyperpigmentation. And again, that's a subject for our next podcast. So look for that coming out soon. So the very beginning of the melanogenesis pathway is the keratinocyte crying out for help, which then activates the plasmin, which activates the melanocyte stimulating hormone, the prostaglandins, which then stimulates the melanocyte. We're going to talk about the first brightening ingredient of the episode right now. And that brightening ingredient is called tranexamic acid. The reason why I'm mentioning it here is because tranexamic acid sits on the plasminogen receptor site on the keratinocyte, basically preventing the formation of plasmin. Without plasmin being created, there are less cellular signals that are going to activate the melanocyte in the first place. So this is what makes tranexamic acid the most upstream inhibitor of melanogenesis. And that also, as we'll see in our next episode, makes it really, really important for melasma in particular. Okay, so first we have stressed keratinocytes signaling to the melanocytes, which causes the melanocyte to ramp up pigment production. Next, we're going to take a look inside the melanocyte to figure out what's happening next. So the pigment we're talking about is called melanin, and it's synthesized inside the melanocyte in a series of enzymatic reactions called melanogenesis. This entire process takes place within a specialized organelle inside the melanocyte. So an organelle is almost like an organ or a tiny little factory. And the one we're going to be focusing on is called the melanosome. So the melanosome is the organelle that creates melanin found within the melanocyte. Okay, so melanosome is that organelle that creates melanin. Melanosomes are unique to melanocytes. They're membrane-bound structures that develop through 4 distinct maturation stages. From stage 1, which is basically just like an empty sac, all the way to stage 4, where that melanosome is now fully packed with mature melanin granules. And the melanin itself is what darkens the melanosome as it matures. So you can think of each melanosome as a little capsule that's being progressively filled with pigment as the melanocyte is creating it. Now there are 2 types of melanin, and this really, they're very, very different. So this is an important distinction. The first type of melanin is called eumelanin. And this is what produces brown and black tones. So this is the dominant pigment in darker skin and dark hair. So I would also just say most pigment is eumelanin in human populations. The second type of melanin is pheomelanin. And this is what produces yellow and red tones. So if you think of a redhead or someone who's very fair and freckly, they predominantly are making pheomelanin, although they also can make eumelanin depending on their genetics. So again, this all comes down to genetics. But the ratio of eumelanin to pheomelanin that your melanosomes are going to create is determined by your genetics, in particular, one gene called the MC1R gene, the melanocortin 1 receptor gene. And I'm going to come back to how that plays into the creation of eumelanin versus pheomelanin in a moment. But now we're going to talk through the actual biochemistry of melanin synthesis step by step. Okay, so we are within the melanosome in the melanocyte cell, and we're creating melanin. So it all starts with an amino acid that you probably have heard of called tyrosine. Tyrosine is a common amino acid found in protein-rich foods. Inside the melanosome, the enzyme tyrosinase, which is the central enzyme of melanogenesis, converts tyrosine into a compound called DOPA. Another little shorthand or cheat for knowing if something is an enzyme or not is enzymes, the names of them often end in ase. So in this case, tyrosinase is the enzyme that primarily interacts with the protein tyrosine. Tyrosinase then catalyzes a second reaction, converting DOPA into dopaquinone. At this point, the pathway branches. Dopaquinone is kind of like a chemical fork in the road. If the compound cysteine is present in sufficient amounts, dopaquinone reacts with it to eventually produce pheomelanin, that reddish yellow pigment found in fair and redheaded people. So again, your genetics will determine if cysteine is going to be present. If it is, in a large degree, most of the melanin that your skin is making is going to be pheomelanin. But if cysteine is limited, and that would be decided by your genetics, dopaquinone then goes a different way. And it's converted through a cascade of different steps involving compounds like dopachrome, which ultimately turn it into that eumelanin, that dark photoprotective pigment that we associate with darker skinned individuals and developing that nice tan. So the end result, either eumelanin or pheomelanin is deposited within the melanosome, which continues to mature until it's ready to be exported. So now we're going to take a moment to discuss how some of the most popular brightening ingredients work within the melanocyte. We already talked about tranexamic acid because that is going to interact at the very beginning of the melanogenesis pathway, blocking some of those initial signals to turn on the melanocyte. Now we're going to focus on those ingredients that are inhibiting the actual melanocyte from creating melanin in the first place. And so this is how I like to educate my clients too. When we talk about a brightening ingredient, it is not going to be erasing pigment. You cannot just go in and remove hyperpigmentation or too much pigment from a cell. The only way to brighten the skin is going to be sloughing off those already pigmented cells. So that's where things like retinol and peels come in, and laser treatments. So these ingredients that we're going to talk about right now are what we call melanin inhibitors. And so what melanin inhibitors do, they're going to be chemically preventing and reducing the amount of melanin that's created in the skin by disrupting that chemical pathway that we just discussed. So again, these ingredients aren't erasing or removing pigment that's already there. We are preventing new pigment from forming in the first place. So think of melanin inhibitors or brighteners almost as melanin preventing compounds. So first up, let's talk about kojic acid. So this ingredient chelates copper from the tyrosinase enzyme. So what that means is it's kind of dismantling tyrosinase chemically, almost like it's disarming it. Because kojic acid works by inhibiting the tyrosinase enzyme, we will classify kojic acid as a tyrosinase inhibitor. Next up is vitamin C. This is the number one brightening ingredient that comes to mind for consumers, but it's actually not the most effective. Vitamin C is actually really hard to formulate with because so many factors like light, air, water can cause it to oxidize and lose its efficacy. If you do manage to use a potent, fresh, chemically bioavailable form of vitamin C, and honestly, you guys, vitamin C could and probably should have its own episode. So if you manage to find a really good vitamin C, then this is how it would disrupt melanogenesis. It will chemically interact with the chemical dopaquinone, which then turns it back into dopa. So that will have the effect of reducing the number of dopaquinone chemicals that are able to continue in the process, kind of like interrupting the flow of the process rather than shutting it down entirely. Next up is going to be retinol or retinoic acid. And this is going to inhibit melanogenesis actually in 3 different ways. First, it downregulates tyrosinase gene expression. So your cells, your melanocytes, are actually going to be creating less tyrosinase. And less tyrosinase means less pigment. Retinol and retinoic acid also speed up cell turnover, which causes the skin to shed those already pigmented cells faster. And retinoic acid, to a lesser degree, also make the transfer of melanosomes to the keratinocytes less efficient. So those are the ways that retinol is going to help brighten the skin over time. Okay, next up, let's go ahead and open the can of worms and talk about hydroquinone. So how does hydroquinone interact within the melanocyte? So number 1, hydroquinone acts like tyrosinase chemically. So it's acting almost like a decoy and binding to the same receptor sites and binding to that amino acid tyrosine, just like tyrosinase would, which prevents the real tyrosinase enzyme from doing its job properly. So that again is going to have the effect of slowing down melanin production, which then reduces excess hyperpigmentation. Another way that it reduces pigmentation stems from the downstream effects of this kind of subterfuge. So when hydroquinone interacts with tyrosine, it actually breaks down and oxidizes, which results in a slow buildup of essentially poison within the melanocyte. So this is known as a cytotoxic effect. In other words, it damages and sometimes kills the melanocyte altogether. So this is a double-edged sword. When you kill off some of the melanocytes in an area of dense hyperpigmentation, that could be a good thing for the patient because they essentially have less of a melanocyte population to create pigment. However, the process of hydroquinone killing off melanocytes can create 2 not so good side effects. And I'm actually going to say 2 bad side effects, okay? The first is called onchronosis, which is a permanent darkening of the skin caused by debris created by these rupturing melanocytes. So when the hydroquinone builds up that poison within the melanocyte, it dies, it ruptures, it releases debris into the surrounding tissue that stains the skin a dark color. So that's called onchronosis. There's also kind of the opposite effect that can happen where there is permanent lightening or like a haloing of an area that's lighter than the base color of the skin. And that's caused by the inappropriate removal of too many melanocytes because you're just killing them all off. So when you kill the melanocyte, 2 bad things can happen. It can either stain and darken the skin through that rupturing and debris, or you can just basically have no pigmentation there, not even matching the base color because, again, there are no more melanocytes in that area. So, side effects like these, along with reports of allergic reactions, are the main reason why the FDA pulled the over the counter or OTC designation for hydroquinone in 2020. It is now only available under the supervision of a doctor by prescription. There were also some reports connecting hydroquinone with cancer, but really experts don't agree on the validity of those studies in humans since they were conducted on rats, and there were very, very large amounts of hydroquinone that were used. So, to a lesser degree, that might have played a role in the FDA's decision, but mostly it had to do with those side effects that I mentioned earlier. So I had a new client the other day, and she said she loved hydroquinone. She got great results from it, but she no longer felt comfortable using it because of what she'd heard. So I told her that while hydroquinone can be a fantastic ingredient for most people, there are many other ingredients that are close alternatives, and when they're used together, they're inhibiting the melanogenesis pathway from a variety of angles, and that can achieve very similar results without the risks of hydroquinone. So, again, instead of just trying to one for one replace hydroquinone with another superstar ingredient, let's use a bunch of brighteners all together that get in the way of the melanogenesis creation from a variety of angles. And then we're going to get pretty darn close to the results of hydroquinone. So, speaking of a hydroquinone alternative, alpha arbutin is essentially a precision engineered version of hydroquinone. It has a little sugar group, like a chemical sugar group added onto it. And that's going to slow the penetration of it into the skin. It improves the stability, and it also eliminates the melanocyte toxicity risk. So it's going to reduce both the rate of melanin production by impersonating tyrosinase, just like hydroquinone does. And it's going to slow down how fast that melanin matures within the melanosomes as well. And the best part, it does not have that cytotoxic effect on the melanocyte, which makes it a safer hydroquinone alternative. So, the keratinocyte's uptake of melanosomes is regulated by signaling proteins such as PAR2, which is called protease activated receptor 2. And that is going to stimulate the keratinocyte's phagocytic activity. So, that's the biting activity. So, this brings us to the final ingredient in today's episode, niacinamide. Niacinamide sits on the PAR2 receptor site on the outside of the keratinocyte. So, in simple terms, this has the effect of reducing the ability of the keratinocyte to create those protrusions that bite off the melanosomes from the melanocytes. That means that niacinamide blocks the transfer of melanosomes at the very end of the melanogenesis pathway, but it actually doesn't have any effect on the creation of melanin within the melanocyte. So once the melanosomes are inside the keratinocyte, something remarkable happens. The keratinocyte positions them in a very specific way. They are going to cluster above the nucleus of the keratinocyte, forming what's sometimes called a melanin cap or a supranuclear cap. This positioning is not random. The nucleus is where your DNA lives, and ultraviolet radiation from the sun is one of the most potent DNA damaging agents that your body regularly encounters. So, by positioning this melanin cap above the nucleus, the keratinocyte is essentially using the pigment as a physical sunshade, which is absorbing and scattering UV photons before they can reach and damage the genetic material below. So, this is what melanin does. It's a photoprotective polymer, and the deeper, richer pigmentation in darker skin types enhances UV protection. We're going to talk about pheomelanin dominant people in the next episode, and for shorthand, we'll just call them redheads. But here's just an interesting fact about them. So, when pheomelanin is hit with UV radiation, it actually creates more free radicals. So it's actually a pro-oxidant, which is why redheads and very fair people who have this pheomelanin gene, right? They are way more prone to developing skin cancer. So it's a double whammy for them. Not only do they not have the protection from that dark eumelanin that's so good at blocking and absorbing the UV, pheomelanin actually causes even more damage on top of that by releasing free radicals. So another interesting fact about melanogenesis in general is that this can take anywhere from 10 to 14 days. So if you have sun exposure, it could take a good 2 weeks for that tan to fully develop. And same thing with post-inflammatory hyperpigmentation from peels or lasers gone wrong. It can take a while for that pigment to form. It is not immediate. And kind of another interesting thing to think about is that the melanocytes in your skin are almost certainly older than most of the skin that they live in. So the epidermis turns over roughly every 28 to 40 days, right? So keratinocytes are born in the basal layer, they migrate upward, they cornify, that means they die, and then they shed off, right? This entire structural fabric of your skin is essentially replaced multiple times per year. But melanocytes don't participate in that turnover process. They are long-lived residents that sit in that basal layer pretty much indefinitely. And stem cells are only sometimes creating new melanocytes. So the melanocytes in your skin right now may have been there for years to decades, and potentially they've been there your entire life in some locations. So this is really interesting because that means that these melanocytes are accumulating UV-induced DNA damage for your entire lifetime. Every bad sunburn you had at age 7, age 10, that left a DNA damage record in those melanocytes that may be still sitting in your skin today. So that's also why even childhood UV exposure is such a strong predictor of melanoma risk decades later. And that's also why we develop hyperpigmentation problems as we get older. Because those melanocytes, after a lifetime of damage from the sun, it's not just keratinocytes that get that damage. Melanocytes also get damage from sun exposure. They are going to start to go haywire and start to behave erratically. And that's how we get hyperpigmentation disorders later on in life. So in part 2 of this series, I'm going to be discussing hyperpigmentation in more detail, the different types, how to treat it, interesting facts. And so look out for that episode coming out sometime soon, hopefully in a week or 2. And thank you so much for joining me today as we took a deep dive into melanogenesis. Please subscribe to Skincare Deep Dive podcast so you can stay up to date with new releases. And if you have any subjects that you would like me to cover in future episodes, message me. So you can find me on Instagram, and my handle is Karen O Education. And I'd love to hear from you. Have a good one.